Okay. So, as an example of a topology, inherited. Burada söylemedim gerçi, değil mi? Şöyle diyeyim, this topology on A is called the relative topology on A, or the topology inherited from the topology on X. Yani X'ten miras kalan topoloji gibi. So here let's consider the following subset. So here I regard S1 as a subset of R2, and in R2 I take the standard topology. Okay, standard topology. So what is the topology on S1 inherited from this topology? Well, I have to just tell you what the open sets are, right? What is our definition? Our definition is that you just take your open sets or in the bigger space and intersect them with your subspace. So my A in this case is just this. Now, what are the open sets of R2? Well, it is not easy to describe all the open sets in R2, but I know what the basis elements of open sets in R2. For example, all these balls, right, are open sets in R2. So an open set is described basically by means of open sets. I mean open balls. So what I will do, just take these open balls and intersect them with this subset. So if you take, for example, an open ball like this and intersect this with our circle, so this is an open set of our circle, okay? Or take this one, okay, and intersect it with this subset, so you get something like this. So basically, just open arcs, form a basis for a topology of your topological space. Of course, one can prove things like this. If you have a basis for a topology, then if you intersect those base elements with your subspace, then that collection will be a basis for the subspace topology and so on. Okay, one can prove such things. They are easy, I mean, almost trivial facts, but they are actually important, of course. Belki şeyi tarif edeyim. Yani in the first hour, I told you, given a space, what I mean, a basis for that topological space. But sometimes we describe first a basis and then talk about topology generated by that basis. So that's something slightly different. Let me give that definition also. Let X be any set, a collection beta be of subsets of X is called a basis for a topology. So here I am saying a basis for a topology, okay? But which topology, I don't know. But there is some topology. There is, so for a topology, if the following conditions are satisfied, what are they? For each point in X, there is some B in this collection so that X is in B and B lies inside. Yeah, that's it. Second condition is the following. If you have two basis elements, and if X is a point in the intersection of these two basis elements, then there is some B3 in this collection so that X is in B3 and this B3 lies inside B1 and B2. Okay? So if you have two basis elements like this, for any point in the intersection, there is a third basis element which lies in the intersection. Okay? In this case, we say that beta is a topology, sorry, is a basis for a topology on X. Which topology? Well, that's the topology just formed by taking arbitrary unions of these basis elements, okay? In this case, let tau be the collection of arbitrary unions of these basis elements. Then is becomes a topology. And beta becomes a basis of that topology, of course. subspace topolojiden bahsetmiştim. Bir başka topoloji elde etme yolu daha var. Yine sıcak oldu. Let f x tau x y tau y be a one-to-one and continuous map. Then the image subset f of x. Of course, this is a subset of y. Has the subspace topology. Subspace topology. If the map, which map? This map. F from x tau x into f of x with the topology inherited from y. So I just take the topology on y and restrict those open sets to my image set. Okay, the relative topology on the image set. Of course, in this case, this map is onto. It was already one-to-one, so it's a one-to-one and onto map. F was continuous. One can check that in that case, this map is also continuous. It is not the same map because I changed the range, right? But still it is continuous. It's a continuous one-to-one and onto map. If it is also a homeomorphism, in other words, if the inverse map is also continuous, then we say that it's a topological embedding. If the map is a homeomorphism, what I mean is this: f inverse from f of x to x is continuous. Then the map f from x to y is called a topological embedding. Okay. So what's a topological embedding? It's a one-to-one map from a space to another space so that f is homeomorphic to its image, where the image has the relative topology inherited from y. Okay, let me give you one example. Now, for example, consider this subset of real line, just this subset, 0 to infinity, okay? And then consider this collection. Consider the collection of subsets. Open intervals like this, where both A and B are positive numbers. And also, okay, this collection of sets, intervals like this, union, here A and B are both positive numbers. Well, it's a strange collection, right? Sorry? B comma infinity, yes. Of course, you know, this collection will be a basis for a topology on X. What kind of sets these are? First one, so here I have 0, and then this goes till infinity. First type of sets are intervals like this, right? Some interval like this, AB. What about this one? This is kind of strange, right? It has two parts. Elements here has two parts. If you have an interval like this, 0 to A, containing this, then you have to take something like this, B to infinity. So you have some B here, and you have to take everything up to infinity. So your collection are this kind of sets, either intervals like this, open intervals, or if your set has to contain 0, then it has to be an open interval like this, but then it has to has a tail like this. Tamam mı? Okay. The first claim is the following. This B is a topology, sorry, is a basis for a topology on X. Of course, on this set, 0 to infinity, we have standard topology. But that's not what we are claiming. We are saying that this gadget describes a topology on the set. It is probably different than the inherited topology as a subset of R, right? I'm not saying that this topology is the subspace topology inherited from R. Actually, we will see that you know, the inherited topology on this set from R is not compact. because this is an unbounded, I mean, you have a sequence of integers which doesn't have any convergent subsequence. But with this topology, it will be compact. Okay. How can you prove this? I will not go into details, but just, sketch of proof. So we have to prove two things. Every point in X should be inside in some B, right? For some B. Well, of course, this is trivially true. Why is that? Because, I mean, if you choose this point as your point, then of course it is contained in this interval plus this set, right? It's a basis element. And if your point, if so X is this point, then it is like this. If X is a positive point like this, positive real number, then I can choose an interval like this. It's also an element of your so-called basis. So you have this. Therefore, this property is satisfied. What about the other one? If you have two open sets, I mean, if you have two basis elements and if there is an intersection point, then there should be a third basis element and so on. But of course, that will be also, I mean, yeah, I mean, we can always do that, right? I mean, there are some cases, but I mean, okay, so let me leave this as an exercise. I mean, this is easy exercise. So what I mean, this, if X is a intersection of two, is in the intersection of two basis elements, then there is a third basis element such that X is in B3 and B3 lies inside B1 and B2. Okay. Now, so we wonder what is that topology, right? What is that topology? Now I will tell you what the topology is. Okay. Now, consider the map. F from this interval with this topology. So let's call this topology form a topology on X. Let's okay. Let's call it tau. So with the topology tau, there is a map into S1 circle with the standard topology on S1. What we mean by the standard topology on S1, the topology on S1 inherited from R2. Okay, the usual topology inherited from R2. And my map is defined this way. F of t is just e to the power 2 pi I t divided by 1 plus t. More specifically, if I don't use this, complex number notation, I can also write it this way. Cosine 2 pi t divided by 1 plus t sine 2 pi t divided by 1 plus t. What we claim is this. This map F claim F is a homeomorphism. Okay. Okay, so you see what happens: 0, infinite, and here so my map is just f of t is just cosine 2 pi t 1 plus t sine 2 pi t 1 plus t. You can show that f is 1 to 1 and onto. Okay. You see this gadget, the map 2t 2 pi t divided by 1 plus t maps the interval 0 to infinity, where 0 is mapped to 0, of course. What about infinity? You never reach the infinity, but as t goes to infinity, this goes to it goes to pi, right? 2 pi. Oh yeah, this goes to 1. Yeah, 2 pi. Sorry. So it goes here like this. And what is this? I mean, and then you go from 0 to 2 pi by cosine and sine, right? So cosine, sine. So it takes this interval. It takes this interval and just sends it to the circle. 0 is this point, and then up to 2 pi. 0 up to 2 pi. Okay. It is easy to show that 1 to 1 onto and continuous. Why it is continuous? Because it's a composition of continuous functions. T over 1 over t is continuous function, cosine is continuous, sine is continuous. So this function is clearly continuous. One has to show that its inverse is continuous. And you can either write down the inverse map explicitly or just look at what the open sets are, you know, how the open sets are mapped. To show that this, so this is my f. I know that this is continuous. We want to show that this one is continuous. So G is continuous. So I have to tell you the inverse image of every open set under G is open. Inverse image under G is just image under F, right? Right? Yani ben bunun open continuous olduğunu söylemek istiyorum F inverse'ün. Bunun continuous olduğunu söylemek için inverse imajların open olduğunu söylemem lazım. Ama F inverse'ün altındaki inverse imajlar F'in altındaki imajlar. So inverse image of a set under F inverse is just the image under F. Therefore, I have to just tell you that image of an open set under F is open. Well, what are the open sets of this topology? Well, I cannot describe all the open sets, but I can tell you what are the basis elements. What are the basis elements? Basis elements, open sets like this, and sets like this. Image of an open set like this under this map, So let me, if you have an open set like this, image of this will be something like this. An open set. image of something like this. And then will be what kind of object it will be? It will be something like this. This union this, and then this gadget, which means something like this. Okay, so it's an open set. Okay. Therefore, this is a homeomorphism. So what we see here, this is a nice example. This gadget with its usual topology inherited from real line is not circle, of course, it's not even compact, but I can just describe another topology on this, and it becomes circle. And the thing is that this open sets, you know, these basis elements are also open in the relative topology, right? But I have less open sets here, not all the sets inherited from R are contained here. I have this strange open sets. Okay, if I have a piece here, I will have something like this. But the thing is that this topology is weaker than the topology inherited from R, right? So let me write as a remark. So if you start with the standard topology on this interval, and if you throw away some open sets, then you end up with the circle. Bir yerde ne yapıyorsunuz? Hani real line'ı üzerindeki topolojiyi zayıflatıyorsunuz. Ya da işte real line'ın yarısını. So you have the half real line and you make the topology inherited from R weaker. You throw away some open sets, it becomes circle. Okay, you change the also, you know, not only topology, but you know, kind of geometry. Which one? This set? This set, this whole, this element. This one or this thing? They're the same set, right? Because of how the pieces. They're the whole three parts are defined. Oh, but it goes under F. What does what look like? Well, actually, here I try to describe. The image of this guy will be something like this. Image of an open set like this will be as follows. This piece will be a piece like this. And this infinite piece will be this part. Okay? Because as t goes to infinity, you are approaching here. Okay? So as a remark, note that the topology tau on X so that X tau is homeomorphic to S1 is weaker than the inherited topology topology on 0 infinite on X from R standard. Yani R standard'dan inherit edilen topolojiden daha zayıf bir topoloji. Ama bunlar comparable topolojiler. Biri diğerinin içinde. Çünkü right, these are comparable topologies because every open set of this tau is an open set actually in the relative topology. It's kind of a strange thing, right? You throw away some open sets and your half real line becomes a circle. Daha fazlasını da yapabiliriz. So this is, you may regard this as, you describe topology and you bend the real line, right? You make it circle. You can do more. You can make the real line a figure eight by just making the topology weaker. So let me give this as an exercise. Consider the real line R with the topology generated by the basis. Şimdi bakayım bunu doğru hatırlayabileceğim mi? Evet. Ya şöyle interval'lar alacağız. Öyle ki A, B'den küçük ve ikisi de negatif olacak. Ya da her ikisi de pozitif olacak. Bir bunlar var. Bir de eğer sıfır içeren bir şey varsa bunun yanında bir böyle parça olacak. Tamam. Bir de böyle parça olacak. Özür dilerim. Şöyle. Let me describe you what these basis elements are. Again, this is a topology on R, weaker than the standard topology, because these are all open sets in this standard topology, but I don't take all the open sets, but some strange looking objects. What are these basis elements? They are open sets of the following type. Either they are open sets like this, usual open set, not containing the origin, open intervals, or something like this. But if your open set will contain the origin, so if it has a piece like this, CD, then it has to has two tails. One like this, an infinite tail, and here A, and the other one is like this. Yeah. No, actually, you know, this can be here. You don't need. You don't need. But to make a, you know, simple picture, I draw it like this. So let me leave this as an exercise. Show that V is a basis for a topology on R. It is weaker than the standard topology, but more importantly, it is the following. Real line with this topology, let's say tau for a topology, let me say tau on R. With this topology is homeomorphic to the figure eight as a subspace considered as a subspace of R2. So in R2 we have figure eight. Figure eight'i çizme şeklimden zaten from the way I will define figure eight, you will see that it is the actually a copy of real line. How? Okay. So this is the origin of the real line. This is the negative axis. You go like this. And as you go to minus infinity, you are approaching to this point. This was 0. As you go to positive infinity, you come like this and again approach to the origin. So it is just the real line banded so that it becomes figure eight in R2. Okay. And with this topology, it is homeomorphic to this figure eight. Here, of course, I draw these arrows, but actually they are, you know, connected. It's just figure eight. So by just changing the topology on R, in this case, you just throw away some open sets. You make real line figure eight. Yani doğruyu bükebilirsiniz. Topolojiyi değiştirirseniz. Peki. Zamanı da bükmüşüz. Pek bir şey kalmamış. Efendim? Orijin nerede? Evet. İyi, bugünlük bu kadar olsun. 4 dakika kalmış. Yeni bir şeye başlamayayım. Evet, sorusu olan var mı arkadaşlar? Evet, yoksa kapatayım ben. Önce kaydı durdurayım. Neredeydi bu?